Hi, everyone.
Hey, Jim.
Hey, Jim.
Hey there. We've got kind of a unique setup today. I appreciate everyone joining. Um, we're kind of divided up. Nick and I are going to stand over here on one side, and then we've got a station around the corner where Jim Weatherwax and some of the people who are joining us. Traffic is just snarled, so a lot of people are just coming in too. So, but I think we will go ahead and if we could, I see Will's on here. Oh, and Andy was going to be on hand, but when you're not on hand, you don't get the beer. So that's the only thing. But I appreciate them logging in remotely. And then Sean and Will from SRC. So very cool.
Good
We will.
evening. We'll send you the bill
guys,
for our beer, Jim. Mm-hmm.
Thank you
There
for
you
joining
go.
us this evening. This meeting, in the previous one, this is the second of 6. And as a lot of you know, what the mode we're in right now with the equipment is really data collection. And when we're still adding instruments and we're actually still learning, some of the new data points and stuff we have trackable. So today is really going to be, we're going to spend a lot of time just going through the operating reports and showing the data that we have accessible to us. We'll review kind of how the system's been operating. Today it got warm, so we were really pushing the system. We didn't have any of the waste heat recovery system operating, so it was just a good natural test. So Damon can walk us through some of those records too, and kind of show how the system performed. And then our suppliers have been such a big part of it, and Super Radiator Coil. Thank you guys for joining, and at last minute too. I'm sorry Ken wasn't able to join us also, but we appreciate the help you guys have done and getting these CO2 coils developed and helping us get these products off the ground. We're still actually utilizing the CO2 coil that you guys helped us develop on the first one. We're incorporating that design into this new setup. So because it's proven so well, but I appreciate you guys being on and sharing kind of what's making your coils work so well on these applications.
Yeah, thanks for the invitation. Looking forward to it.
Very cool. I will from our team, we're going to have Damon. As I mentioned, Damon will be presenting and taking over from it. Jim Weatherwax is on the screen out there around the corner. He's here on site facilitating. And then we appreciate our host, Nick Gislason, and we are going to again he's got a lot of questions for Damon too as we get into this also. So look forward to the interaction, and please, this is we're kind of feeling our way through it. We're in the process of this. Any questions you guys have are just super important. We're transcribing this. I don't know if it's recording actual video, but we are transcribing it, and that's for just to help us with follow-ups and all the AI help in that regard. But with that, Damon, why don't we take it away?
All right. Thanks, Jim. Thanks, everybody. Appreciate everybody being on. And I'm gonna start.
We didn't do a toast.
You got a
I should do a
toast.
toast. Yeah. So
There
if
you go.
everybody has a drink, yeah, let's raise it up, because we're into month 2, so, and it's going good. So we're still toasting.
Awesome.
So cheers, everyone.
Cheers to that.
Thanks.
I wish this was a Hanabi lager.
Oh, the beer is so good too.
Water works okay too. Awesome. Well, I'm gonna jump in and I've got a few different screen shares that I'm gonna share with everybody. I'm gonna start with the first one's gonna just be a P&ID overview, so process and instrumentation, and I'm gonna kind of just quickly focus on where we're taking all the heat out of the brewery, but then we gotta get rid of all that heat that we recover, or get rid of it, and we're getting rid of that through the gas cooler. And that's where I'm going to introduce or have Sean and Will introduce themselves, and we'll talk a little bit about the gas cooler, the design of it, where its pressure limitations are, and kind of in comparison with a standard synthetic refrigerant coil. From there, we'll look at, I did a 2-week look back of the operating parameters and how the system's been operating, both from a mechanical refrigeration standpoint as well as from an electrical standpoint. So we're recording all the electrical data that's coming in from a consumption standpoint, as well as multiple data sets through the Danfoss controls. And we've got a really nice summary of that. Then we're going to look at kind of a summary of what a daily report looks like and get some information on that, as well as a daily consumption report on the electrical side as well. So I'm gonna share my screen, and we'll take a look at this P&ID. And along the way, if there's any questions or input, just feel free to let us know.
One update I can share with you, Damon, is Mylin from RD Winery next door. She gave us the go ahead on the KW monitoring, so we'll get that equipment hooked up. So
great. Does everybody see the screen okay? Is this coming across all right?
Yep.
Okay, excellent. So I just did some HTML outputs to everything. So these are just different tabs as opposed to running a spreadsheet or a PowerPoint or what have you. So the P&ID of the system, we've got the 2 compressors. They're piped in parallel. Our discharge pipe is this red pipe here. It's discharging up. It goes through some oil management system. And then it goes through, hits a valve, which makes a decision. Do I need heat recovery? Do I not? And we can talk about that as we go along. But ultimately, that refrigerant ends up in this gas cooler / condenser, I'm going to call it. That's got our 2 fans on it, and that's where we're cooling this refrigerant down and sending it back to the system. Once we come out of there, we go into some of the low pressure stuff. We do some refrigeration. We can talk a little more about that if we have time. But for right now, I really just want to focus a little bit on this gas cooler portion of the system. And Super Radiator, both Sean and Will represent Super Radiator, and I'd like to let them introduce themselves, and then we can have some discussion about the gas cooler.
Perfect. Well, I'll start, and then maybe I'll turn it over to Will, who's been the kind of the lead engineer on this project. So I'm Sean McCandless, Director of Sales Engineering for Super Radiator Coils here in the Richmond division, and lead the engineering team here, and certainly happy and proud to work with Pro for I think the last kind of 10 years or so. And then Will Klick, he's been the lead engineer on the Pro account for a number of years now, and he's going to take the lead on explaining how the coils work.
Thank you for the introduction, Sean. So yes, the gas coolers we use for this, we're actually able to, let me share my screen here. We're actually able to share almost the identical coil as your non-gas or your synthetic refrigerants. So from the outside, this is your synthetic refrigerant coil, and this is your CO2 coil. It'll slow today, but it'll flip over. Physically, if you're just looking outside, they are almost identical aside from a slightly larger connection here. But what makes the CO2 coil much different on it is internally the tubes are substantially thicker. So you're going from a 020 wall, or sorry, an 014 rifle tube all the way up to an 035 thick tube. So your wall thickness on those CO2 coils is 0.035. Makes it a substantially heavier duty coil, gives you a little more robustness, but also it can hold that pressure. So the CO2 coils like this, we can actually rate up to about 2000 PSI or 140 bar, which gives us the pressures you need to handle that CO2 load. So even if you're got the unit sitting outside on a 120-degree day, it's going to hold the pressure of a standstill on that without any issues. It also, as Damon said, it's kind of gives the unit a little bit more robustness. So even though the one they're working with them, that first coil we built them, has been put in a couple different systems, moved around, probably beat up a little bit as technicians have moved it through the different units. it's still robust enough to handle all of that movement. Part of this as well with the CO2, we have to go through some additional processes on it. We can't safely test it pneumatically. So with air up to the 2000 PSI, you'd be putting a bomb in there until it's formally tested and proven. So we have to do a hydro test on this. We flood all of these with water, pressurize them up to the 2000, and then we have to run through a specialized drying process that Super Radiator has developed to get all that moisture out of the system and keep it clean and fresh for your refrigerant so you don't have any issues there. Those are the main things that make the CO2 coil a little bit different than your traditional synthetic refrigerant.
Nice. So we're pressure rated, Will. We're tested all the way up to 2000 PSI.
So the ones we designed for you guys, because we were using the XHP header, so the copper alloy header, those are rated to 1740 PSI, so 120. But we can easily switch that over to a stainless steel header. I believe one of our variants we did for you early on actually had that stainless header, and that would get rated up to 2000 PSI.
Nice. Lots of options available there.
There are. And if you ever run something where you want to go higher than that, we can investigate it. We'll have to get into steel tubes, but we can handle it.
Nice. That's pretty cool on the construction of everything with the coil. And is the material, I know we've got a thicker wall material on the tubing running through the coil. Is the tubing that's running through the coil just thicker copper, or is it also like a copper iron alloy?
So we've run through a few iterations on that. We actually started with a material called Unalloy, which the first unit you guys received from us was made out of Unalloy. That was a copper iron alloy. Long story short on that, Carrier bought the mill that was producing that and decided they're no longer going to make it anymore. So since then, we have gone through, redesigned, retested, and got our ULs for using just a plain copper, just extremely heavy wall copper for it. And we can do those in 5/16 tube, 3/8, or 1/2 inch. So we've got a wide variety based on the system size. So if you guys ever decide you want to make a extra large unit, double your capacity, we can go for that 1/2 inch tube and get a lot more out of it. Or if you start to look at smaller ones, we can drop down to the 5/16 and meet you there as well. Gives us a lot of versatility in the system. But now
you mentioned.
Sorry, go ahead.
No, you go ahead. You were going to explain the headers.
Since you're talking about the alloys, the header is made of XHP or K65, depending who you talk to, same material. It is still a copper iron alloy, and that gives it that 1740 PSI rating.
Gotcha.
Is that still a popular choice in the industry, or is it shifted more and more people going all stainless or going to a stainless header?
I would say the majority we're seeing is K65, especially right now. The biggest market for these systems or for the CO2 gas coolers are grocery stores, and most of the grocery stores are just piping in K65. So.
You mentioned UL, Will. I know that came out. Is that our testing or our safety rating standard that we're certified to?
Yes, we're certified through UL 410.
Okay.
Yeah. So all of our CO2 units are certified through UL. And again, we can do that both at the 1740 or the 2000 PSI number.
Awesome.
Yeah, because I remember initially we did have the stainless headers, right? Then we switched to the XP.
We did. There was a short time there when, due to some contract stuff, XHP was not available in the U.S. They were switching over from K65 to licensing it through Mueller, and Mueller just hadn't gotten the supply chain up and running, so we had to use the stainless until that got sorted out. But been a few years now, and things seem to be very streamlined on it.
Well, we appreciate your guys' patience as we've grown this business, and hopefully you're seeing it grow in other areas also. We're sure excited about the interest.
Yeah, you guys were some of the earlier pushers on us for it, and we've seen a lot of growth in it. Again, the grocery stores being the biggest, but we've seen in water heaters, some going into some commercial applications, and starting to see more and more hitting all over. So it's it's a great market to be in right now.
Right on. Cool. Well, is there anything else about gas coolers or condensers you think our friends and people here would like to know?
I mean, I think one of the biggest things to know about them is the glory of the CO2. It's future proof. As we go forwards, the synthetic refrigerants are just going to continue to phase out. It's kind of a given at this point. We've probably got about another 5, maybe 10 years max on the refrigerants we're using today for the synthetics. So in my view, you might as well start working on that CO2 for a long-term system that's going to last you into the next generation.
Well, let me ask you a question. So there are features in this product that have kind of made it robust, more robust for the application, in addition to the tube.
Right. So
you want to point some of those out? Mm-hmm.
Sure. So a little bit on our design beyond just the CO2 specific. So we have these added on both the synthetic and the CO2 versions. But over the years, we've added brackets onto the headers. Let me jump to the 3D model here. So we've added a number of features on here to help make these systems more robust in general for PRO's lines. We've added the brackets to the headers. We had some times in the past where either through expansion or manhandling, headers were being damaged and it was causing issues to the system. So by adding the header brackets that on our traditional systems are brazed into it, that's making a more robust build for the overall. We've also gone through, and it's going to be hard to see on here, but we've oversized all of the tube, or all the entrances for the top 2 circuits, so that if you have a little too much hot gas flooding at the top of the coil, you might get some more expansion than you would normally expect. We've added those to avoid any type of rubbing on the tubes and protect the system with that. Beyond that, in our shipping processes with you guys, we have whiteboard that goes over across all the fin to protect the surfaces so that when it gets installed and ends up on your unit, you've got a nice, pretty product and not a bunch of bent over fin that's not as attractive. Those are the main features we've added. In addition, we've made the casings a little more robust, thickened them up, and some of those methods.
It's almost like I knew the answer.
You would think.
It's been a good partnership. We've appreciated working with SRC, and your factory just 5 miles or 5 hours up the road has been a benefit also. But,
it has. I've run a few coils down to you guys on the back of the truck, so it's worked out well.
Yeah.
Hey, Will, well, we've got you guys, and we're talking about the gas cooler / condenser. Could you maybe just do a quick rundown of why when we're talking with CO2, it's not just the condenser, the mechanics in the field, what people know that's a condenser. Why are we calling it a gas cooler and a condenser and mixing the terms up? Just seems like it makes it more confusing.
It does. And to be honest, it took me a little while to understand it. But the main reason why you call a traditional system a condenser because your refrigerant, as it goes through the system, it's condensing. It's going from a vapor when it enters at the top of here, works its way through the circuits, cools down, turns into a warm liquid. On the contrary, on a CO2 system, the entire way through it, depending on the operating conditions, it's going to be a gas. So it will enter as a superheated gas and leaves at a slightly less superheated gas. It's still staying in that gaseous phase, though, which gives the CO2 a lot of options that traditional refrigerants don't have, for options like the heat recovery that you guys do, where you salvage a lot of that waste heat into your water systems. From ours, we also see a lot of that with the reheat systems on grocery stores. So you'll use it as a hot gas coil in your air handler, which might even be an option you guys could investigate in the future as well. If you've got air handlers heating your space, you could bypass some of that waste heat and dump it into your space. So instead of dumping into atmosphere or putting into the water like you're doing currently, you could bypass that into an air handler if there's one close enough, and you've got a hot gas reheat system. That's one of the big benefits. You get that great heat recovery off it, and it's a substantially higher temperature, so you're getting a lot more usable energy out of it.
Nice, nice. Thanks for that.
Of course.
Right on.
Do we want, if, are there any questions from anybody else on that side of the system? All right. Well, I'm going to go ahead and I'll start sharing my screen and I'll jump in and we can look at some operating reports and then take some questions as we go through that. Nick, you look excited to go through this.
For sure.
He's asked me like 4 questions today, and I'm like, boy, that'd be a great one to ask Damon online. So
Yeah. Yeah. Nice, nice. Well, and if there's, as we're going along, if there's anything in these reports that we don't have available, I'm connected with the system, so we can always get those answers. The first report I wanted to show is an example, is our daily operating report. So we're taking all these data points from the system, and then we're generating a report. The report gives us, and I'm just going to run across this across the top. You know, do I have any current active alarms? This high PC, that's my condenser pressure. So I want to just have an idea. If I'm above 1400, I just want to know. It's kind of a call it a soft alarm, if you will. What's my glycol average? Hey, the glycol temperature that's feeding the brewery, that's what's, you know, important. This is like my suction superheat. How am I protecting that compressor while I'm running? That's a number that's important to us. And, you know, we want to stay above 20 degrees, of course, with that. But, you know, if we get too high, that can mean things. If we get too low, that can mean other things. But at 25.2 degrees in this case, that's a really nice average for operating suction superheat. This receiver pressure, I want to know what that is, because the receiver / flash tank, that's another one of those components that we've got multi names for on a CO2 system, but essentially it's just a receiver. But I want to maintain that pressure as close to stable and where I tell it to be as possible. And so our average receiver pressure was 544 PSI. This average gas cooler pressure, that's what was the average pressure in my gas cooler condenser, you know, what we were just talking about. You know, I was averaging over a 24-hour period yesterday. I was averaging 902 PSI. Then I want to know, you know, how many times am I starting these compressors? You know, you don't want to start them too much. You don't want to start them too little. There's kind of a sweet spot that you're looking for. Then we're pulling in some information from our energy system. So, you know, what was my kWh consumption over the last 24 hours? And then adiabatic runtime. What did it look like when I was calling for the adiabatic system to run? And that's just we didn't talk much about that in association with the gas cooler, but it's a wetted surface pad that we evaporate water as it comes across and reduce that air temperature in versus out. So the gas cooler, we kind of make it think that it's running in a lot cooler climate than it actually is. Alarm side, everything's good. This 74, like right now, I've got no active or acknowledged alarms when I pulled my report. I had 74 alarms. That's something to note there. Those are all low pressure alarms. Those are soft. We can talk about order of operations and how we shut stuff off, but essentially what we do is at the end of a refrigeration cycle, when we don't need refrigeration anymore, we close some valves automatically. The refrigerant pressure comes down and it hits that number, and that's what shuts the compressor off. So those aren't like any kind of nuisance or anything like that. My glycol reservoir temperature, it's stable. My lowest it saw was 18.5 degrees Fahrenheit. The maximum it saw was 24.5, and I averaged 21.5. Overall, I'm flat, stable. It's happy. Gas cooler condenser pressure. The lowest I got was 728 PSIG. The highest I got was 1,459 PSIG, and I averaged 902. There was about a 5-minute window in the last 24 hours where I was above 1,400 PSI. Then jumping down to my flash tank, my receiver, what was my average pressure? The bypass valve, that tells me a lot, like what's happening with that bypass valve. It peaked out at about 26%, but it's averaging around 1.3%. That's so I'm not generating too much flash gas. My flash gas coming into my receiver isn't too hot, so I'm not wide open. So I've got a good stable flash tank pressure. Suction superheat, we get information on that. And then this is kind of neat with where we get on the compressors. Like we could look at our compressor runtime. So over 24 hours, the compressors were only running for 102 minutes. We started 29 times. Our peak highest capacity we got to was 100%. And between compressor 1 and compressor 2, they each ran 1.4 hours. So there's a lead lag the way it operates. We start one compressor first, and then the next run cycle we start the other compressor first. So those should always be even. Then we looked at the energy system and pulled that information in. It looks normal. I'm going to jump up and I'll talk about these 2 flags where it says, hey, review. You might be having some short cycling. These are things you can look at to dial in the system better. The energy system, we used 88.8 kilowatt hours while the compressors were running. That totaled 56.2 kWh. And while we were baseline energy is what we're calling it here in this particular report, but that's when we weren't running a compressor. So we were running fans potentially. We were definitely running a process pump, and the circulation pump could stage on or off. Heat recovery, we look at the heat recovery, SHR3, SHR4, those are our fluid temperature on the water side coming in and going out. And then what was our heat recovery storage tank temperature? Doesn't look like we were doing much with heat recovery in the last 24 hours. And then looking at our pre-cooling on our adiabatic. So we've got the relay in the control system said, hey, I want you to run for about 447 minutes. The temperature coming in was 92. The temperature going out was 92. So the report says, hey, you've got something that's not right. We should be 10, 15 degrees cooler with our air coming out. So take a look and verify your water supply to your adiabatic pads. And Nick and I've already texted on it. We've had some discussion on it, and that's one thing we got to get sorted out. So this is a daily run report that we generate off the system with all the data we're capturing. There's more data sets, more data points that can be grabbed. This is just what we're getting started with right now. Any questions on any of that? So it's a lot.
That's good. Thank you. How many systems are you pulling data from?
How many systems, like overall, like all CO2 systems in general, Jim?
To create this report? Is it
2.
just the MyHydro and the Danfoss?
Yes. Yeah. So just the Danfoss information and then just the MyHydro. And when you look at the reports from those systems, every system that you're utilizing kind of has its own unique way of giving you the data. It can be like it is data overload. So we've worked with some other tools internally to feed those data sets into a tool that says, here's what you asked me to build you. And it's very flexible. It's nice. This was one thing we wanted to look back on, was say over the last 2 weeks, how has the system been performing in relative to its capacity and the load? So we're doing some estimation points on you know, what I don't know the brew schedule on site, but I know how the demand is on the refrigeration system. So, you know, what can I get? And you know, we had over the past 2 weeks, we've ran the refrigeration 7.5% of the time. We've had 403 compressor starts. We've averaged about 74% capacity, and the glycol reservoir, it's been running between 18 degrees and 25 degrees. So it broke down just a little bit further for me, and this is kind of neat. It's kind of an interactive little, you can see when I hover over these little boxes, it gives me data. But it took the all 2 weeks, and then this is a 24-hour window across here, but it highlighted some boxes and said, hey, here's where you had some peak load that was outside of your averages, which is kind of cool. I get these daily run minutes and starts. So, you know, we can see how many starts we had on each day and where was our peak load day. So looks like on June 1st, we had a pretty heavy operating requirement as opposed to the rest of our run times.
Interesting.
And then just looking at it, we can look at like an hourly load profile that's an average over the 14 days as well, kind of where are our peaks and valleys in a 24-hour period. So I don't know if that aligns much with Nick, but I would say Monday, June 1st, we probably put a pretty good load on the system.
They don't have a microphone over there at their station, so.
Gotcha. Maybe a little knocking out, maybe a brew day, something like that.
That's interesting.
So we took we just to dive in even deeper with all the access to all the data points we have, took that energy system. So, you know, and it over a 24-hour period, based on the information you get from the energy monitoring system, we could dig into that even a little bit further. And I thought this was pretty neat because this is like over a 24-hour demand on the system. And then it also tracked, you know, what was my capacity on the rack. I call it a rack because it's a rack controller, so some of the words are playing over. But even though I've got two compressors, how much 0 to 100% cooling demand did I have? And I can see that when I had a higher demand, I had a higher electrical usage. That's what you would expect to see. This was kind of neat. It overlaid this tan window here and said, well, here's where you this is where you had a dry pad, an adiabatic pad. It's making an assumption. It's saying, well, I don't think you had water on those pads because I think your temperature should have been down, and I think you could have come in a little bit lower. So we're getting some predictive analytics with our reporting system too.
That's exactly that. They hadn't finished installing the pads, right? So
correct.
It was
We're still
reporting
working
exactly
out
as
the
it
water
should, yeah.
supply. Correct. Hourly energy consumptions we can get, and just kind of you know, just an overall view of the energy system, you know, over the past 24 hours. Sorry, I'm moving around there we go. You know, now we take a look at the energy information that we had over the past 2 weeks. So it kind of overlays with that 2-week load summary, and we just get a daily energy analysis or consumption. What did we consume over 14 days? You know, when I'm running compressors versus when I'm not running compressors, what's my standby consumption on power?
That's interesting.
Yeah, it is. And this is all right now, kind of what I said a little bit earlier. It's like data overload. There's so many data points. There's so much coming in. You know, we're probably between now and our next Pro Green 50 meeting. That's where we'll have refinements. We'll focus in on certain data sets and start dialing things in from there. Any questions? Nick, you had some questions that were saved.
I think they're getting Nick's attention. He was curious, and I think they're bringing him in. He was curious about the highest pressures that the system saw, and kind of how it handles that. And I think you covered that. We're unfortunately, we didn't realize that we're posted up by the air compressor, but there are. So I'm not sure he heard.
We don't even hear it on our side. It's super quiet.
But I know that the high pressure was one of Nick's questions. Here he is.
Question time.
Bring it.
Well, let's see.
Refrigerant sight glass question.
Yeah, just a low, in the nitty gritty question, but I noticed that in the receiver tank, the lower float is not floating anymore. So
Yes.
something I'm not sure if that has to do with the heat today, because it's certainly hotter today and yesterday than it has been, but that's something we've noticed.
Yep. So what's probably happening, Nick, is because we're running at these higher pressures, we're getting the higher temperatures. We're not running heat recovery. We're not running adiabatic. And so what that's doing is we're elevating those temperatures. So there's some other valves in the system that are starting to pinch down, throttle back. It's dialing back capacity. We're probably getting higher oil carryover. We're probably getting warmer flash gas into that. And so we're getting bigger oil carryover rates. I wouldn't add or go to put anything into the system. I'd check it and see how it looks in the morning.
I see. Once it's cooled
odds are,
when we were looking at it, it wasn't running either. The system was between cycles also.
Okay. And that's and I've seen this before. It'll look if you get too reactionary, you say, man, we need to get a jug of refrigerant in this thing, even though because the pressures aren't telling you that. The pressures are telling me, hey, if I was low on charge, I wouldn't be able to hit 1600 PSI. I wouldn't be able to cool the system down. I'd be cycling off on pressure. So it's telling me that I just got some refrigerant at different spots in the system right now. And then once everything settles down overnight, it's going to end up back in that flash tank.
Yeah. And now we'll see if you can hear me all right.
Yeah, we get to hear you really
compressor
good.
running, but we'll step away a few feet here. Can you hear me?
I sure can. Yes.
Okay. So I guess the other question is, so we have that visual indicator of that little float. Now, is there any other indication of if we actually truly are low on refrigerant, let's say there's a leak or something, between now and the point at which the pressures drop off, in which case we're kind of like in deep shit, at that point?
Yeah.
Is there any way to know where we're at in between now and then?
Let me think about that for just a second. Visually, that you're going to see on site, no. Mechanically, how things are operating, yes. We would see the average refrigerant suction pressure start to trend down. We would see discharge pressure likely trend down as well. We would see, and I'm just going to throw out a few others. We would see the expansion valve position probably trend higher than normal. And we could see the flash gas valve during operation start to trend smaller. So we're not getting the flash gas built up, so it doesn't need to open up to bypass that excess pressure because it's low on charge.
Got it.
And the expansion valve on the evaporator, it's saying, hey, I need more gas, and it's trying to take gas. So it starts opening up, saying, hey, feed me, but we're not feeding it. So there's just some trended patterns that we would see.
So with a trained eye, we'd be able to pick that up. I'm not sure myself quite yet. I would pick up a trend like that.
And we're going to need to get smarter in the controls too. Because like you said, Damon, the electronic valves, they'll auto adjust and you won't even notice that the
That's
system
right.
is,
That's right.
is low
You
on
could be
refrigerant.
running low and you wouldn't even see
Yeah.
it. You just because it's making its adjustments. The high
So-
pressure valve's another one, and then that all kind of correlates to that's like what Will was explaining earlier about with a CO2 system. Aside from the gas itself, but you've got control valves that are different. So on a synthetic system, we don't come out of the condenser / gas cooler. We don't come out of that and hit another valve. We just go straight into the receiver and then we go
Right.
into our expansion valve. With a CO2 system, we go through a high pressure valve, and it's kind of to just make it super simple from my perspective, it's kind of like having a second expansion valve upstream of your expansion valve, because
Right.
it makes an adjustment, it regulates everything downstream of that valve is insulated because it's cold. And so when
Right.
we do that, we generate that flash gas, and that's what we got to get rid of. So though how those valves are all working and trended and how they have been working are some pretty solid indicators to like, hey, we might have a leak. One
And I
other
wonder-
one, if there's a big leak, there's a CO2 monitor built that's inside the system, inside the cabinet. And I want to say that ambient CO2 ranges are something like, it's a value of 275 to like 3.25. But if there was like something catastrophic that happened inside the cabinet, and there was an immediate release of CO2, it would register that on that CO2 alarm. You don't see it outside of the cabinet, but if you're looking at the alarm, the display will turn from green to red.
Yeah.
So if you find that while you're there and looking around at it, it's just something else you can take a peek at.
Yeah. Now I wonder, with as sophisticated as that control system is, if there's some way that you could program it to tell us if it thinks there's a leak, because that all the valve positioning you explained to me, I understand that you could pick that up having looked at thousands of these things, but as a user,
Sure.
it would take, I think, me quite a while to develop that level of understanding of, okay, if this valve, then this valve, then this
It's like
valve.
4 things.
Right.
Yep.
Yeah, exactly.
The beauty that I can't do it inside that controller that I'm aware of. But what I can do is on the daily reports, we can flag that as something that we're looking at. And
As a
then
baseline. Yeah.
honestly, we're letting AI do all the work for us, guys.
Right.
Because that's what let it crunch the numbers. We'll just tell it which numbers to crunch.
Right. All right. Well, moving on. Another couple like pretty core questions. And one of
Yes.
these actually came from a visitor that we had that came to look at it a little while ago. And it was a really basic question. It says, well, CO2 compared to traditional refrigerants, how do they compare as far as kilowatt consumed for BTU of cooling achieved? And if you see what I'm getting at, how much electricity do you have to burn to produce a BTU of cooling? And obviously that changes, I'm sure, on air temperature and, a lot of factors. But let's say for, over the course of a year, if you had all else equal, the exact same facility with the exact same work pattern, the exact same loads, everything, would the electricity cost be the same or higher or lower for CO2 compared to traditional refrigerant? Which I thought was a pretty valid question.
Yeah.
Sure,
And also
sure.
kind of a hard one to answer, maybe.
It's a very complicated question. And I get asked, and I'm always told, like, you're making it too complicated. And at the end of the day, you know what? I'm going to try and make something very complicated about as simple as I can. If you look at it over a 24-hour period between the two refrigerants, all else the same, not considering the controls and all the stuff, and we're just talking the gas, okay? You can make CO2 be a little more efficient than a synthetic refrigerant, because with CO2, when the temperatures are coming down in the evenings and stuff, you can take advantage of what we call subcritical operation mode. And so I can get a lot more work output from the electrical energy input. Okay. But during the heat of the day, I'm running transcritical. Now, as a system, you go, well, that's when I should be recovering all this heat into my heat recovery system. But if I'm trying to compare the just two gases alone, and that's all I'm looking at, then I say, well, okay, well, I can get to 250 degrees gas temperature with CO2. I can get to 160 degrees gas temperature with the other 448 or 449. I'll use that as my example.
Right.
Well, I run a lot hotter and I'm a lot happier. I'm more dense with the refrigerant with CO2. So my line sizes are smaller. I have less system charge that I have to contend with. But at the end, 50 horsepower is 50 horsepower that I'm trying to turn a motor over on. And so the rest of it's like, how does your control system and how does the system in general get utilized? So, I think it's almost tricky question because it is complicated. It comes down to the system.
Yeah.
What do you think, Jim?
I was going to say we did an independent case study with CalNext,
There you
and
go.
on that case study, we did kind of what we're doing here. We just got permission from the winery to put the KW meters on there, but we had a synthetic based chiller that we monitor the KW usage and then our CO2 chiller, and then looked at them head to head over a extended period of time. And what they found in the summary of the case study was head to head, the CO2 system did operate more efficiently over the course of it. It wasn't, but as Damon pointed out, it wasn't because head to head CO2 is better than R449. The reasons was because we have VFDs on the compressors. It's because we have electronic valves, because we're adjusting the flow of the glycol, and we just have much better, tighter system control. We were eliminating the compressor cycling. I think all of that was the reason there was no sacrifice in efficiency when you did compare them head to head, but it did take the controls and, so there was an added investment. Does that make sense?
Yeah. Yep. Definitely.
And then as we all know, kind of the cherry on top of the main thing is the waste heat recovery. But setting the waste heat recovery aside, another thing that was important to us doing that independent study, and we'll put a link to it. We'll throw it in the chat here too, if you guys want to look at it, because in the past that was, you had to sacrifice, you had to pay more to operate the CO2 system, but the benefit was you got more heat recovery. But it was important for us to prove that you didn't have to sacrifice, and the third party, this independent study, it did show that. It helped us prove that.
Yeah, so I think it's more of like a life cycle cost.
It did. This was in California, so it looked at the whole seasons too, the high temperature and the low temperature. In the summer, the synthetic based system was a lot more efficient. In the winter, though, the CO2 more than made up for it. And that was all factored and outlined in this report.
Got it. All right. Well, moving on to a question about the hot water recovery. So we had that up and going. We had a big production run about 2 or 3 weeks ago, and so we had it. We were experimenting with it in 2 different ways. One where we were feeding water directly through. So I guess I call like a one pass, where ambient temperature water goes in, and then hot water coming out, getting collected in a tank that the volume is accumulating as we go.
Okay.
And so call that like single pass.
Yep.
And then alternately, we're doing some trials with a recirculation on a tank that on purpose we're trying to stratify. So letting the hot water stay at the top and drawing and heating the colder water from the bottom. And so we're working with it in both ways. But something that we found was that since the load was varying over time with the chiller, and at least in our brewery, it's not steady. It's different, every hour of the day, sometimes more, sometimes less. And without any flow control on that water, then our temperature out was all over the place,
Okay.
right? Which
Okay.
makes sense
Yep.
because it's
Yep.
like in the single pass, if you're putting in it's 60-degree water, you've got to be able to regulate that flow to maintain 180 out. It's just
Yeah.
a flow regulation. And so I think
Yep.
thinking about it, we need a modulating ball valve or something that's sensing that temperature on the HX out and is modulating
Uh-huh.
to control the flow to maintain that 180, because that's an important number for us. If it drops down,
Yep.
it's not so useful. Obviously, if it goes higher, it has its own problems.
Well, we have VFD
But-
pumps on there too, can't we? We should be able to adjust the flow of them, right?
Well, the one caveat with that is they're a centrifugal pump. And so I think that would work when we were doing the recirculating heating, because the head, it's you're just pulling from the tank and returning. But when we're doing the one-way water, that wouldn't work because it would just free flow through the centrifugal pump.
Okay.
So it really has to be a valve, I think, at least for that, for one pass
Yeah,
mode.
and that is precise.
Jim and I were kind of brainstorming stuff a few weeks ago about it. There's a valve there's an energy valve that incorporates an actuation, and you tell it how many BTUs it can do, and it's got flow meters and stuff. And there's something we're going to be investigating there.
I think that sounds like a pretty elegant solution or a sophisticated one, but I think earnestly, even just a temperature sensor in that outlet pipe with the water and like a 4 to 20 controller that can just modulate the output of that valve position. Something simple like that might be enough.
Yeah. No, for sure. Well, there's more capability in the existing control system of that. It's just something we'd have to investigate that.
But that would be one thing to make that hot water really useful for us. Some way to control that 180 output, because otherwise it was almost impossible because the load varies so much. It goes from 100% to 10, 20%,
Yep.
So it was hard to get the water, the temperature that was useful for us exactly.
Like get it dialed in.
Yeah.
Yeah.
Unless we had
that
somebody
makes sense.
just sitting out there on the valve,
Yes. Yeah, that's not great either. Right?
No, we don't have extra people for that. But that was a couple of my main ones about dialing in the hot water recovery, certainly being a big feature. This chiller, that would be good to get that honed in, and then the kilowatt per BTU question that I get is hard to answer, but it might be interesting to think about some experiments we might be able to set up to probe that maybe a little bit. I don't know. Do some thinking about it.
Yeah, no, for sure. I've got that stuff noted. So no, those are great scenarios. Great questions, man.
Groovy.
Will, Sean, did you guys think, was there anything, from a gas standpoint that you had any input on or any thoughts on? Did it seem like Jim and I got it summed up pretty good?
Oh, you guys did great.
Yeah, I think you did great.
Yep. Appreciate the invitation, and just next time we got to do it with a few beers.
Yeah.
That's right. We'll get beers remotely next time.
Yeah, Ken says he wants some East Coast of these events, so it's definitely in our agenda. We hope to do more of these, but these are great, and I appreciate everyone who tuned in. But yeah, unless there's anything else, we can probably wrap this up, don't you think? Or are there any questions?
Somebody asked a question in the chat. I saw that earlier. It was from Michael. Asked about comparing CO2 with NH3 or ammonia. Well, I'm gonna just lead with my chin on this one. I'm not a big ammonia guy. I'm just not. I know a lot about CO2 and I know a lot about synthetics. I hear a lot about ammonia. systems. I think that it has its place, and there's similarities on where it's utilized, but I just can't tell you that I can speak that well to that.
It's efficient. We know that, but it is a different beast. But we also said
Yeah.
we'd never do CO2, and here we are. So
That's right. That's right.
I do see a future with, A3 and, those are the three refrigerants out there: ammonia, CO2, and propane.
I'm still out
And
holding out hope,
isobutane.
Jim, that you're going to be working on propane one of these days.
What's that?
I said I'm still holding out hope that you're going to be working on propane one of these days in your future.
We definitely will. I can guarantee that. I mean, our A2L
Yeah.
line will neasily convert, or not easily, nothing easy about it. But
Nothing's
no,
easy
we'll,
about it.
we'll
It's the
definitely
next
be,
step.
we'll be right there when it happens. We won't be as pioneering as we have been in this path. But we're excited about it. Yeah, it's coming. We know that.
I would add maybe just a couple of things on that ammonia versus CO2.
Yeah.
There's certainly
Please.
the safety aspect, which maybe Damon is why you're maybe a little hesitant to it. I think from a coil standpoint, you can't use copper with ammonia coils. And so that drives you into stainless steel. And so then you're going to be kind of 2, 3, 4x the price of a copper system like what Pro uses today. So it might be a better refrigerant, and maybe kind of more operating efficient, or operates more efficiently. But I think cost of system is going to be a lot higher, and just going to have to weigh that versus the benefits.
The total
and in
cost
addition
of-
to the system cost, there's the overall system and safety costs with it, because once you start putting ammonia in there, it's a heavier than air gas that is poisonous. So you have to have a lot of alert systems out there. Ventilation has to be greatly increased. It becomes a whole nother world of safety requirements. So
Can you
That's
make
a great
180-degree water with ammonia?
I'm not sure.
I'm not sure on that
heard
one.
Propane is good.
I don't know.
I don't
How about
know.
no? For this call, no.
Yeah, I
Yeah.
don't think so.
Definitively
It's
no.
not even worth checking. Yeah.
Somebody would jump on that though, but I don't know. Awesome.
Right on.
No,
Well-
great question. Thanks, Michael.
Well, they got a whole nother meeting going on over there, so it's good. So I'll join them. We got a bunch of people who are now getting here on site. I think traffic finally let up, so we'll have a follow-up group here. But what a great call. I appreciate the time from everybody, and yeah, this is good. Thanks, Jim.
Thanks, everyone.
Thanks, guys.
Great.
Have a good night. Bye-bye.
Thank you.
We'll talk soon. Thanks, Nick.